So welcome everyone. Today we are very happy to have Katz from Boston. He's going to tell us about QFT in real time.
Thank you very much for the invitation. Great to be here, see old friends. Yeah, so we're talking about different work that I've been doing in the last few years with a kind of overarching theme of trying to understand dynamics in quantum field theory, but in real time. So this is work that various papers that I've written with the authors here, including your very own Luca. We're trying to understand a way of thinking about a new way of trying to parameterize dynamics of quantum field. So on a very basic level, the goal is to almost go back to childhood and try to solve quantum field theory, at least in some numerical approximation. That is to say, really solve the Schrödinger equation. We're trying to simulate the world of a particular quantum field. And when you start thinking about this problem, the first question you might want to ask is, well, how do I parameterize this world? How do I think about the Hilbert space itself? So this is one of the things that I'll try to explain. So first, I want to try to say that a promising direction of thinking about the degrees of freedom of general quantum field theory is to essentially think about embedded into some sort of underlying CFT structure. And as I'll try to say, it's a pretty universal way of thinking, but at the same time, we've also found empirically that it is a practical way of thinking. Then I want to say a few words about the relation between the method that I'm going to be using to simulate quantum field theory. It's a method called Hamiltonian truncation that I will explain. And I want to talk a little bit about its connection to Lorentz invariance and the challenge of doing things in a Lorentz invariant way. I'll talk about a few just particular quantum field theories that I personally found kind of interesting. And I'll describe to you observables that we can now compute in these quantum field theories. And then the bulk of the results that I will talk about are work that, in fact, I've done together with Luca, where we try to explore high energy states in a quantum field theory and try to understand how is it that closed systems thermalize, right? So we're trying to understand ergodicity and so-called eigenstate thermalization. Okay, so first of all, kind of the CFT perspective. So the idea is that we try to think of all quantum field theories as some sort of CFT perturbed by relevant deformations. And I think this perspective, first of all, has a kind of appealing structure to it, because as is very well known in CFTs, there's an operator state correspondence, which means that the structure already has within it both kind of a map of the Hilbert space and also a set of local observables, ways that you can perturb the system, ways that you can probe the system. And once you take the CFT structure and then you're deforming it with a relevant deformation, so you are kind of flowing towards the IR in some RG flow, you're guaranteed kind of in a C theorem sort of spirit that these degrees of freedom of the CFT are all you need to describe the degrees of freedom of the full QFT. So by embedding it into a CFT, you already kind of mapped out the territory in a certain sense. We have an inner product on these states and so on, but also mapped out the observables. You have access to local observables together with the Hilbert space. So I just find that personally appealing, but as I'll try to show you, it's also practical. The way one starts thinking about it is that the QFT dynamics is computed in this basis. So in the basis of states which are dual to local operators by the operator state correspondence, and the matrix elements of the Hamiltonian in that basis can be computed entirely using the CFT data. So that's kind of the nice
So you
thing.
think about this as perturbatively close to the CFT, so
No,
you want to go potentially far away?
yes, I'm not doing conformal perturbation theory. That's very important. So of course, I'm only going to do it numerically. Right, but the idea is that this is the space we live in, and then we attempt to approximate states in a gap theory. But indeed, the entire hope, and I'll show it to you in various lower dimension examples, is that if you give me this set of data, that is the data of a CFT, namely the scaling dimensions of all the different operators, and the OBE coefficients for these relevant operators, that's really all I need. That's all I need to parameterize the matrix elements of this Hamiltonian, and also, as I'll try to show you, all I need in order to compute the energy spectrum of this quantum field. The challenge, I will say right away in this method, is that computing this data is quite difficult in general, even in theories which are integrable or free. In practice, because there's always an exponential number of states, you have to come up with clever algorithms in order to extract this. So this entire method is always the hill that you have to climb is always computing this data.
Just to go back to this other point, there should be some notion of closeness in some sense. At least I'm confused about it. Because couldn't I take my CFT and often embed that in a Gaussian theory and view that as some relevant deformation? Often there's some Gaussian theory flowing to a non-trivial CFT and then flowing.
I agree. Very good, very good. So that's a point I was literally going to make later. Yeah, you kind of want to take, ideally, especially for numerical practicality, the kind of closest CFT you can get to, right? So for example, like I'll talk about the Ising model, and it's best to start, if you want to perturb the Ising model, you don't want to do 5⁴ tuned to the Ising and then exactly. Right. In principle, you could, but in it's not the most practical. So let me just flash for you kind of a hope, just so we understand, so that I give you kind of a North Star. We're not far, not close to this, right? There are a lot of things that we still need to compute, but I must say that we're coming closer to, so for the first time, we can start thinking about 4D CFTs and their deformations. The various ingredients are coming together, but just as a kind of North Star, which we hope to get to eventually, this is what QCD is for us. So QCD is take QCD, add a bunch of flavors to the point that, for example, you have 15 or 16 flavors. That is a CFT. It's a CFT because the fixed point coupling is small, so it's reliably a CFT. And then get rid of all the extra flavors that you don't want, right? Maybe if you want to just have the up and down, get rid of all the extra flavors except for 2, right? So that's our concept of what QCD is. So it's a relevant deformation in the CFT, right? And this is conformal, as I said. It's people believe that it is conformal. Again, the crux is who's going to compute the data for this theory. In principle, one could compute it perturbatively, but it's not an easy task. And so the cartoon is kind of like this in this kind of stories that in the UV you have the CFT with its data and its set of states, basis states and local operators. And then you add this deformation, and so there's some mass scale associated to this deformation. The dimension of this operator when the coupling is weak is of course going to be close to 3, but not exactly 3. And so there's some scale at which this system breaks, and below this scale you lose these extra flavors, you get log running, and in an exponentially small scale further down, depending on the coupling, you get QCD dynamics. So of course it's not perfect QCD, it's polluted by relevant operators from that scale. But I think as I'd be ecstatic if we can get, right? So that's kind of the idea of how we should think about QCD. And the point is that the data is entirely gauge invariant. So you don't have to choose a gauge or worry about breaking gauge invariance with some cutoff. All you need is the data of the CFT. If someone gives it to you, you can start doing the computation observables. Of course, in practice, this is very difficult because this data is not available, but recently work in n=4 super Yang-Mills at large N has given us hope that it's a good place to start. There's already a lot more interoperability machinery. People have written codes to compute the data of n=4 super Yang-Mills at large N. And so you might hope that some SUSY version of this is something that one could try to do in the next year or two. All right, so that's kind of the big picture. So now I want to tell you a little bit about the way our Hamiltonian methods relate to Lorentz invariant. So first of all, the method that I'm going to be using is part of a general class of methods called Hamiltonian truncation. So you take in general, the Hamiltonian written in some basis, and you truncate to a finite subspace. So of course, in a QFT, it's an infinite space, but you truncate to some very large finite subbasis, subset of the states, and now you have a very large matrix, and you diagonalize this matrix, and that therefore you get some sort of set of approximate eigenstates and eigenvalues. So that's the technique that we're going to use. And the advantage of that technique is that very often you could arrange for a truncation, if you're think about it a little bit, that preserves some subset of the symmetries, translation invariance, or rotation invariance, sometimes supersymmetry. So that's kind of the nice aspect of this method. But for every given problem, you might have to think about what kind of truncation is more efficient. That is to say, which truncation more readily gives you access to the low energy states. So in some sense, there's no, it's a kind of a trial and error. And the main challenge of this method, as all methods that are really attempting to diagonalize the Hamiltonian, is that there's a very rapid growth in the number of states. And so efficiency is very much key. And much of what I'm going to show you is in lower dimensions, primarily because of this, right? Like the more states there are, the more difficult it is to extract the data associated with these states. So it's crucial to look for more. And just as a bit of a lesson, just to make sure that we're on the same page, because very often when we think about quantum field theory, we think in terms of Feynman diagrams or in terms of some perturbation theory or summation of perturbation theory. I want to kind of make sure that we're on the same page as far as how Hamiltonian methods work and how their connection traditionally to the complexity of the computation. So let's just take a very simple example. Let's say 5⁴ in 2D. And so, if someone told you, well, use truncation to solve 5⁴, this might be your first approach. You take the Fock space basis, right? You have a bunch of bosons, they have some amount of momentum, you put them on some circle, and so their momentum is quantized, and you might just choose a truncation by which you never consider momenta above a certain value, and you restrict yourself to some number of particle states that renders a finite subbasis of the full Fock space, and you might want to compute. Then you compute the Hamiltonian in this basis, and then you diagonalize it, and you get approximate eigenstates in terms of the Fock space basis, right? But what I'm interested in is the relation of what you would get to the volume. So this is our truncation again. So we're restricting ourselves to some number of particles with some bound on the momentum and some bound on the total number of particles. And now I want to ask, what is the relation of that to our usual scheme of computing using Feynman diagrams? So usually with Feynman diagrams, we take some observable and we expand that observable in a power of the coupling. And so you might think to yourself, well, here's a scheme that computes things non-perturbatively, but I should be able to match to the answers of the perturbative expansion if my coupling is weak. So I could just take this in this truncation, and we can numerically compute this quantity x. And then the question is, what happens when we take the volume L large? Do we recover Feynman diagrams at infinite volume? Do we recover in some approximation these Feynman diagram coefficients as we take the volume to infinity? So I mean, imagine that you took like, I don't know what, 30 particles is the maximum. And then you could perform this computation on your computer with maximum number of 30 particles. You recover Feynman diagrams up to corrections that come from this UV cutoff element. What say you? And apologies to the experts who obviously know the answer to this question. Do you or you don't you? How many people say yes? Okay, the answer is no.
Yeah.
You don't, right? Why not? Well, because of the orthogonality. So the orthogonality catastrophe says that it essentially requires an exponential number of particles, right, to recover there's an exponential suppression once you go to large volumes between the vacuum, the original Fock space vacuum, and the new vacuum in the presence of the coupling. So there's an exponential number of basis states just to capture the vacuum at large L. And that's not just something specific to the vacuum, that's true for all eigenstates of the interacting. So it's kind of shocking, but it's true that what you would have thought naively is a polynomially difficult problem, computing, I don't know, Feynman diagram with some finite loop expansion, turns out to be an exponentially difficult problem in the case of this kind of Hamiltonian method. And another way I can motivate this is to just remind you that the boost operator in this one-dimensional thing is a combination of a free part and an interacting part, and this interacting part violates particle number. So there's no way that at any finite particle number, you will ever recover Lorentz invariance.
So what does the first equation mean? I thought that the vacuum state, we could just choose it to be normalized. Why do you have the e to the minus L there? What do you actually mean by that?
Well, I just mean you in the Hamiltonian, you have the original Fock space vacuum, right?
Yes,
And now you diagonalize the Hamiltonian and you find the new ground state.
yes.
And this is the overlap of the old ground state.
Oh,
with
it's
the
an
new-
old, it's sorry, it's not zero lambda, I see.
Yeah, yeah. Yeah, sorry, maybe my notation is- Sorry. Some people use this notation. Yeah. And so it's not surprising that you can't recover a Lorentz invariant Feynman diagram by restricting to any finite particle number. And so, you know, it's kind of an interesting question just to ask, well, wait a minute. I feel like I'm a little bit lied to. I mean, are Feynman diagrams really a perturbative expansion of any kind of quantum mechanical Hamiltonian framework? Certainly not the one that I told you about. The answer is yes, and it's something called light cone quantization. So I want to explain a little bit what quantization is, because it's an attempt, the way you should think about light cone quantization is it's an attempt essentially to recover some amount of efficiency when you perform Hamiltonian methods. So for that, I want to explain that the light cone is really very subtle effective theory. Unfortunately, we don't really understand the full rules of the game because it has non-local terms. It's a little bit like sket, if you're familiar with it. But we did some numerical experiments and we certainly understand it in certain cases, so which I'll show you. But I want to explain to you what is the kind of question that light cone asks as an effective theory, and I'll give you, again, answers for certain cases of problems, but I do not understand how to formulate the effective theory in generality. So imagine that, again, we're going to, just for simplicity, I'm going to stick to 1 + 1 dimensions, so it's kind of easier, and it's also where we have the most kind of set of numerical experiments, so I have some sense of what's happening. But the idea is essentially that you have theory on a circle, it's translation invariant. You could, of course, consider any momentum sector. And now you can ask, what happens as I take the momentum, the center of mass momentum, to infinity, right? So I'm on a circle, I have a discrete spectrum, so I expect this to be my set of energies. And what I can consider is something called the light cone energy. It's the difference between H and P. And notice that this difference actually is suppressed with P as P goes to infinity. And at some point, it essentially tends to zero compared to the characteristic scale, which is 1 over the volume. And so you get a pileup of states near zero. And so there's a natural effective theory that whose degrees of freedom you might identify, which is, why don't you just start with states that already have P plus equals to 0, because essentially as P goes to infinity, those states are arbitrarily close to the what you're looking for. So this again suggests that somehow a CFT is thinking of things in terms of a CFT is a good idea, because if you think of the Hamiltonian again as a CFT plus some relevant deformation, then a 2D CFT always has a chiral sector which has P plus equals to 0. For CFTs that are just particles, this just means that you're choosing, let's say, left-moving massless particles. So there always is such a sector in a 2D CFT, and what we're suggesting is that those are the degrees of freedom of our effective theory. And the conjecture that we
Wouldn't
have,
most CFTs have only the vacuum as the chiral sector?
sorry,
Wouldn't most 2D CFTs that are not rational have only the vacuum as the chiral sector? Like
no, I mean, you always have the
the stress
Virasoro,
tensor, you're
yeah.
just talking about the stress
Yeah,
tensor?
I'm just talking about the chiral descendants of the Virasoro. Like just take the vacuum and act with arbitrary powers of the I don't know, left moving part of the stress tensor.
But that's something that's completely determined by symmetry.
The set of states, yes.
Yeah.
Right. Right. That's right, but you know, as I'll try to show you, the Hamiltonian, I don't always know how to compute in that sector, but indeed, it's a sector that always exists. So the idea is that there is some effective Hamiltonian, light cone Hamiltonian, that only acts within that subspace, only acts within the Carless Virasoro, like left-handed descendants in the vacuum or in the chiral sector. And it has the exact same physics in the large P limit of the full theory. For example, it has the same eigenvalues and has the same correlators. But in practice, especially in 1 dimension, 1 plus 1 dimension, this is if someone gives you this object as a gift, that's a huge, it's an exponential increase in efficiency, because instead of basically thinking about left moving modes and right moving modes, you truncate to just the left moving part, and that's much better.
So basically you're at scales way above any relevant deformation in the story, just looks like a CFT.
Right, but the first, I mean, as I'll show you, in the beginning, you're adding a relevant deformation, and then you're also boosting.
Then you're also, okay.
And then you're also boosting. So, but at the end, as I'll show you, the effective Hamiltonian knows about the scales. So what is the structure of it? And I'll give you some examples. So you add a bunch of relevant operators, and what you get, what does this effective Hamiltonian kind of look like? It has a bunch of light cone operators, which are non-local. So there's still, that's kind of the difficulty in determining this effective theories, that we don't always know how to compute these objects. And then they have coefficients that depend on the original couplings, but also on the vevs. Right, so in particular, if there's some interesting phase transition of vacuum structure, it's going to be sitting in the vevs. It's not very different than what you do in the perturbative limit of, some theory where you have spontaneous symmetry breaking, right? Then you first use semiclassics to compute the vev, and then the vev becomes a coupling in your Hamiltonian, like for example, 5⁴. If you have a, double wall potential, you're sitting in one of the vacua. Around that vacuum, you have a phi-cubed coupling that depends on the original parameters, right? The vev enters as one of the couplings. So what I'm trying to tell you is that we have evidence that that's just universal. It's not just in this kind of in cases where you have some simple semi-classical. And the nice thing about that is you basically recover a Lorentz invariance in the sense that the boosts become kinematic. And they no longer, the boosts are in fact the boosts of the original CFT, and that this effective Hamiltonian obeys this Lorentz alpha. So very naturally, this object actually annihilates the CFT vacuum. But it's not the case that things are easy, because remember that the vacuum structure is contained inside of the couple. So we don't know how to compute this for all cases, but I'll give you one example where we do, which is this case where you have a relevant information whose dimension is less than 1. In that case, this is the answer. D goes to infinity. We can show computing matrix elements that the answer looks like this. So let me explain. So this is the VEV of the operator. And when the dimension is less than 1, this is going to be some well-defined object. It will depend on both the coupling and on the volume. So in some sense, in this infinite momentum limit, it kind of in a subtle way remembers that it's in finite volume because it depends on this VEV. And then, okay, this is the operator integrated over the light cone. And this thing is, for people who know about 2D CFTs, is kind of the natural kind of state that at infinity, it's the the properly rescaled operator taken to infinity that comes from the inner product. So this entire operator makes sense when you measure things within the CFT. Yeah.
Sorry, this VEV is VEV in which theory?
This
The deformed theory.
deformity. So it's non-zero, it depends on the dimensional parameter.
I see. So that is A part is something unknown to begin with.
Yes, so in principle, I mean, here, of course, yes, so if, that's right, so you need to be able to fix this from, if you want to set the scale in this particular theory, you need to fix it from something else. But of course, since it's the only dimensional scale in the game, it's kind of,
I see.
it's also not interesting, but sometimes you know what it is and then you could check it. That's
Why doesn't it generate other operators?
I have to show it to you. It's because when you start, I mean, it's a technical thing. You contract to compute this, the dominant effect at infinite P is a double contraction with this operator when you compute a correlator. I mean, it's a technical thing. I don't want to get into it. This is the dominant, it generates a bunch of operators, but all of them are suppressed by P. So at infinite P, they all go away. That's what we found. And we have various numerical checks.
So maybe this is the P to infinity that I don't understand. So what does it actually mean that this becomes this operator at P equals infinity?
Well, you take this theory,
That's a theory, I guess.
yes, on a circle, right? And then you consider states on at finite P, and then you compute, let's say, you compute the spectrum of the P plus operator as P goes to infinity. And the claim is that spectrum is which acts entirely within the chiral sector reproduces the spectrum of the full theory, including both left and right moving pieces. All right. Okay, good. So as I was trying to suggest, the truncation that's sort of natural here, like the way to think about the theory is not necessarily in terms of Fock space basis. Especially we saw that, here, we had kind of naturally an object that has only a kind of an easy interpretation in terms of the CFT basis. I don't know necessarily what this means, for example, in Fock space basis. And so it suggests that the way that you should really think about the Hilbert space, as I said, in this case, we have only chiral states. So you take the chiral operators. Again, these are the chiral Virasoro things in the chiral Virasoro block. So you take the chiral operators of the theory, and they have a natural inner product and so on. So they're your space. You compute the matrix elements of the Hamiltonian, which I wrote for you, for example, for that particular case, in that basis. And then the truncation that we are suggesting is to truncate the dimensions of these guys to some maximum. So that's the truncation that we're suggesting. It's unusual because it's a truncation on a dimensionless parameter, but we find that this is an efficient truncation that allows us to compute the data. So this is what I'm going to show. So for instance, you could sort of try in some sense, a non-Lagrangian theory. So the easy model, of course, is just a fermion, so it does have a Lagrangian, but if you deform it with the sigma operator, that's a complicated operator in the fermionic theory. The fermion, for example, field doesn't have a simple equation of motion. This operator is not some kind of thing that you could write down in terms of the fermionic field in any kind of simple way. So in some sense, I would call this a non-Lagrangian theory because it's not a simple operator. Now, this is, however, a very famous theory that Zamolodchikov has solved. It has a set of spectra, a set of states, and by the thing that I told you on the previous slide, we claim that this is the Lycombe effective Hamiltonian for this theory, and then we can compute it. So for example, we compute the eigenstates, and because one of the things is about once you have the eigenstates, you can compute dynamical quantities, like for example, a form factor, right? So you could take the trace of the stress tensor between, this theory has 8 bound states famously, and you can compute the form factor of these bound states. So here I'm showing you this computation. The dashed line is our data. The solid lines are the results from Zamolodchikov. So you see a very good agreement, even though you don't have that many states in the game. So this is kind of an implicit check of this formula. So you can compute dynamical quantities. You can also compute correlation functions in real time. So this is the Fourier transform of the Lightman function. And again, Zamolodchikov famously argued that if you integrate this 2-point function, that gives you a quantity which is a C type of C theorem. This quantity only increases, measures the degrees of freedom in the system. And so again, one could compute it using integrability and using our data, and you see that it has very good agreement. It asymptotes to a half, notice, because the UV of the theory is just a free fermion. So it's C equals a half, but here you see all the structure that comes from various bound states in this theory. And we see that our numerics are reproducing it. And if you compare various quantities like the masses or the contribution to the C function from the first, second, and third bound state, you see that the agreement between our truncation and integrability is very good, despite the fact that at this truncation level, we only have less than 500 states. And getting to this kind of agreement using standard methods, right, where you have both left and right movers, requires tens of thousands of states, and I don't think they ever reach this kind of agreement. So it appears to be a very efficient technique, efficient because you're essentially cutting down on the number of states already by just going to this Lycombe limit, and then the basis itself seems to be efficient. So once you look at this kind of, once you convince yourself that the general framework is right, I can just tell you just for fun, there's a sort of theory that now you can explore non-integrable models, like the ones where you have both an epsilon and sigma deformation. The epsilon deformation is just a mass for the fermion, so this is an integrable deformation by itself as well. So this is kind of a very nice model because it's a sort of model that you might see in some of the first type of, I would say, quantum computers that would simulate a field theory, right? So people have these spin chains or qubit models, and this is kind of the easiest model that they could try to tune to criticality to find, and we are able to compute various things in there. In this case, we understand, we have evidence, numerical evidence, that again, if you boost the system, that you get an effective Hamiltonian. Again, like only the left movers are capturing the degrees of freedom, except we don't understand, because different phases of the model have different vevs, we understand this model only in the so-called broken phase. So in the broken phase, this is the effective Hamiltonian. So we're kind of, if you were to interpret this model in terms of phi to the fourth language, we're doing, we have a double well potential and we're breaking the Z2 symmetry. So there's a little bit of an asymmetry between the two wells. But this is a very fun model because there are kinks that go from this vacuum to the other one, a kink and an anti-kink. And when the potential is perfectly Z2 symmetric, there's no force between them. But the second one of these vacua becomes more advantageous, this vacuum costs, and that creates essentially a linear potential between them. So it's a kind of very simple model for confinement. It's like a toy model. So here I'm going to show you the data that we computed. So we can, again, we compute the Weightman two-point function of the stress tensor, the spectral density of the stress tensor. And I'm showing you the spectral density profile as a function of energy this way and as a function of the coupling that way. So this is the coupling, sort of 1 over the coupling. This direction is weak coupling. This direction is strong coupling. This point here is this integrable magic E8 point. But now we're able to compute the spectral density in all these different regimes. So we see stable bound states, and we have predictions for these bound states values that potentially could be seen in an experiment. And then also we find something kind of surprising, just for fun. That's one of the reasons I chose to show you this model, is that it has stable bound states, again, because there's a kind of a linear potential. But once you cross the 2-particle threshold, you would have expected the bound states to fall apart, to become resonances, yet these resonances appear to be incredibly narrow, even though the coupling is of order 1. To explain this, but this is just kind of a fun phenomenon. Once you have an ability to measure widths of particles at strong coupling, this is the kind of phenomenon that you could discover. So how is it that these guys are narrow, even though the coupling is order 1? I don't really know, but it's just kind of fun.
So can you distinguish your resonance? Let's say you didn't know that at 4m squared they should not be stable. Could you have told just from the data that some of these are resonances and some?
Yeah, so what Zimolodchikov actually did is that so there was already numerical evidence because Zimolodchikov computed in a very he approximated this model as having only a 2-particle state. And then he found the energies of those 2-particle states. And of course, here it makes sense that these bound state energies are capturing the data, but he essentially numerically, even here, you found some state which is kind of very close to what you would have thought is an unstable particle. So there was kind of indirect numerical data that before, so that's why we weren't like shocked when we saw it, but I mean, it was still interesting to see that that's true. All right. Good. So just a very quick other thing, there are many models I can tell you about, Schwinger model, all kinds of models that we've looked at. But one model which I kind of think is just fun because I can just tell you the story very quickly is the so-called Cinch-Gordon model. It's a well-known integrable model in 2D, deformation of a scalar, which we are now able to compute. And for a long time, this model had a conjecture duality because you could solve this model using these fancy 2D integrability techniques, which essentially leverage the fact that there's only 2-to-2 scattering. So you should think of this model as kind of the integrable version of phi to the 4th, right? Phi to the 4th has like a repulsive interaction and no bound states, but it's not an integrable model. Whereas here you have 2-to-2 scattering, but there's nothing else except for there's no particle production. So you can solve the S matrix, and the way that the S matrix depended on this parameter B, it very clearly had a B goes to 1 over B symmetry, but it was not known, there was no, how do you check that the actual Lagrangian or Hamiltonian that you've written here has the exact same duality symmetry, right? You have to actually solve the model non-perturbatively in order to do that, and it proved to be too hard to do using other methods. I mean, clearly using the lattice, this is impossible, right? Because there's nothing, I mean, you have to tune an infinite number of coefficients to realize Koch, right? It's not an easy thing. It doesn't have an obvious universality class. And so, but with truncation methods is something that you can check, and in particular, what we did is we computed the moments of the spectral density of the stress sensor, which is something one could do, and we found that all these different moments seem to be symmetric around the point 1. And also, in particular, you can't even see it, I guess there's a red curve and a black curve. The red curve is our data, the black curve is the result from integrability. And therefore, we see that, you know, across the board, all these moments seem to be symmetric, indicating that indeed this theory is self-dual. So this is the first time that I think there's direct evidence that this is self-dual. Anyway, so that was just fun. So let me talk about the bulk of my results, and that has to do with looking at high energy states. So that's really something where a method like truncation or any method that looks at Hamiltonian method has kind of, it's a new frontier because it's difficult to obtain this without looking at the Hamiltonian. And so the idea is to look at very high energy states of finite energy density, much bigger than the typical mass of particles. And so there is an idea that, well, this is kind of like our world, right? That it could be a closed system, but it's still the case that a very large energy state is kind of like a thermal bath. And so it should have an emergent temperature. Apologies to the experts, but how many of you know what the eigenstate thermalization hypothesis is? Okay, about half. So, okay, you could tell me to speed up, but for completeness, I just want to make sure we're all on the same page. So there's this very clever question that Sridniki asked, which is how is it that temperature emerges, or maybe how is it that thermodynamics, how is it the systems go to equilibrium? And he said to himself, okay, let's start with some initial state, with some, let's say, average energy, with some spread, and evolve the state in time and measure some kind of local operator. That is to say, an operator that measures, that only has access to a few degrees of freedom in the system. What can we say about the dynamics to make it consistent with what we know about systems reaching equilibrium? So he assumed, let me assume that any state, initial state that I consider, which has some kind of energy, well-defined energy like this, should arrive at some kind of equilibrium state with some sort of density matrix. So what are the properties that the dynamics should have? And one thing that typical studies in chaos first you should know is that there's energy repulsion. So when you look at this expression that I wrote down, at late times, basically everything where n is not the same as n oscillates away, and you wind up with this expression at long time. And so how is it possible that independent of the coefficients here, this expression is the same as that expression? And he concluded that one possibility is that the equilibrium arrives due to universality. So in other words, these matrices, if you take an eigenstate of a sufficiently complicated system, then measuring a local operator in such an eigenstate is already should give you the equilibrium. Right? That was his idea. And for large volumes, also because we think that the canonical and the microcanonical ensemble approach each other, that should mean that there should be, for a particular energy, large energy state that has some finite energy density, there should be an approximate temperature that I should be able to associate with it. And so the idea is that temperature should somehow emerge, and we should be able to extract the temperature by measuring some local operator in some very high energy. So the idea is that a complex energy eigenstate is already a thermal bath. And this is a very nice story, very, I think, deep insight, and it has been checked numerically for a whole bunch of different systems that have finite number of degrees of freedom, particles or spin systems. But in what sense is this story true? So that's the question that we're trying to answer. I mean, first of all, QFT data is not usually quintessentially discrete, except for CFTs. That's an important exception, which is very interesting. And this high energy data can only be computed numerically. by discretizing the QFT in some way, right? But of course, when you're discretizing the QFT, you might be making all kinds of arbitrary choices like boundary conditions and so on, putting in something in a box or maybe using light cone-quantization or whatever. So this data that you would compute, when you compute this, will always be partial and approximate depending on all kinds of choices that you make. And it's not obvious that it should be consistent. And the other question so this is just kind of a technical thing, like is the mechanical reason for the fact that we see systems reaching equilibrium when they're quantum field theories, is it the same as when you have theories with a finite number of degrees of freedom? And the other question is kind of more dynamical. Are there non-thermal bath states? Can they dominate in some region? Can we like if you when you have a thermal bath state, if that's the only kinds of states that you have access to at high energies, then all initial condition memory is going to be erased. But are there some kind of long-lived states that keep the memory of the initial condition? So in some sense, I want to try to rephrase this for those of you who are EFT aficionados in a kind of EFT sense, right? So when we are looking at the ground state, the vacuum, we're used to kind of the following sort of thinking, right? We have a continuous, say, spontaneous symmetry breaking, we have an order parameter for that breaking, and because we have a non-zero value for that order parameter, we can predict what it would be like to excite that state, right? And we know something about the fact that we have Goldstone bosons, right? And we can predict the IR behavior of the correlator due to the fact that there's a non-zero value for the order. So we have a sense that there's we can think of this, the degrees of freedom, as being parametrized by some Goldstone boson effective theory, right? And I think it's kind of an interesting question, to what extent is any of this true about high energy states? And there's been a lot of progress recently. So first of all, you could measure, for example, instead of measuring operators in the ground state, you can measure them in an excited state. What sort of operators should you measure? Well, you measure these local operators and the state is thermal, then you might expect that every single operator is given by its thermal expectation value. And if that is the case, then again, you can make some statement about what it's like to excite that state, right? So the excitation of that state should be the same as exciting, measuring a local operator in a thermal bath, which tells you that it has non-trivial IR degrees of freedom, namely hydrodynamics, right? And this is kind of very cool, something that we know, and there's a lot of work has been done, including by Luca, on developing this hydrodynamic effective theory. So there's a kind of analogy there, whereby you have emergent degrees of freedom, and they're emergent from this high energy state. But in practice, even though we think it's a very robust behavior, I mean, in some sense, hydrodynamics is more universal than Goldstone bosons, right? But from the perspective of theoretically trying to understand this emergence, we have not been able to develop the tools before that could see this, right? Because it's effectively non-perturbative, right? You really hydrodynamic regime happens when you have many, many particles that are in this very complicated high energy state, and they are transporting energy in some coherent way. So even if the system is weakly coupled, because you have so many particles, it doesn't matter how weakly coupled it is, right? QED still has hydrodynamics, even though the coupling is 1/137. This kind of high energy state data is difficult to extract from a Euclidean lattice, right? It's very Lorentzian in nature, and so even computing things at finite temperature in real time is quite a challenge for them. It's a very Lorentzian kind of physics, and so precisely the kinds of methods that I've been discussing here are kind of ideal. So what we're going to do is be very humble, again, because there's an exponential growth in the number of states. And so we would want to see any evidence for, maybe we haven't seen evidence for hydrodynamics yet. I can give you the punchline, but the first thing you'd like to understand is whether there's an emergent temperature. Do states even look like they have a chance of having hydrodynamic fluctuations. And so we're going to take this phi to the fourth theory, and we're going to compute its high energy states. And we're going to ask, is it the case that the expectation value of a local operator in this high energy state is approximately given by some emergent temperature? And then we're going to try to understand the predictions of chaos. Like, for example, does random matrix theory play a role? So we're going to do it again in our kind of model where we are taking this original model and now we're modeling it with this effective light cone Hamiltonian. We understand that this is the right, in fact, we can map these parameters to this parameter here, as long as we say on one side of the phase transition. So we understand that now. The basis of operators, again, are the chiral states. So these are, in this particular case, simply if you want operators with many, many fields with derivatives on them. These are the chiral states of this C equals 1 CFT. And if you're less fancy about it, you can think of these as just some set of orthogonal polynomials in Fock space. So this is going to be our basis, and we're going to truncate this basis. And so first I'm going to tell you the results. But in order to understand the results, I have to tell you a little bit about what is the regime of validity. Where do we trust our results? And our philosophy was, well, the first thing we check before we look at this eigenstate thermalization is we just try to understand the thermodynamics, and we try to see whether the thermodynamics is healthy. And in the regime in which the thermodynamics looks like it makes sense, those are the states that we trust to do our numerical experiments over. And the subtlety comes because we are doing this truncation in a dimensionless parameter. And so we have to discover what are the emergent UV and IR cutoffs. And what we found effectively, I'll show you a plot, is that the size of states turns out to be energy dependent. The volume depends on our truncation parameter, but different states of different energies essentially have different volumes in our scheme. And the way we measure the size of the state is the way we measure the size of the proton is we measure a form factor again. So we can compute, take some state, feed some momentum into the state, and we take the limit as the momentum transfer goes to 0. And by doing this, we can extract the size, right? The coefficient of that computation is the size. And we can check whether, if we are right, that the scaling goes like this, then this coefficient alpha for different states should be about the same, right? So, and that's indeed what we see. So what we see is that for all the different states that we are considering, their value of alpha is about constant for the majority of the states. So they do indeed seem to have a volume which depends on the dimension of the energy. And so therefore we can identify the energy density with the energy squared over. And when we do that, we can plot just the entropy density, right? And here it is. This is the entropy density for this theory of different truncations. And we see it's supposed to, according to the Cardy formula, it's supposed to go like the square root of the energy density. And we see that it follows that up to a certain point where we basically run out of states. And then in the IR, we also have some sort of truncation effects. And so there's a regime over which there's kind of a robust thermodynamic behavior. Also, we've checked more. We looked at the speed of sound. We looked at other thermodynamic observables. This one's just kind of the easiest to explain. And so we identified some regime over which we think our states are healthy. And then we can then first ask, well, does the spectrum have chaos? And there I just, again, excuse me for the experts in the audience, but I don't know how many people in the audience have thought about quantum chaos. So I want to say a little bit about why random matrix theory is part of quantum chaos. And it's kind of, you could think of this as a sort of quantum butterfly effect. So imagine that you have some eigenstates with the energy which is within some band. And there's an exponential number of such states, right? And imagine that you computed these eigenstates, but then that you modified the Hamiltonian by some tiny, tiny perturbation. Then what does chaos mean? Quantum chaos means that there's a maximal rearrangement of the state. So a tiny perturbation means that if I try to take the new states in terms of the old states, there's just a maximal rearrangement. There's some basically, they all just get rearranged order one with some kind of random matrix here, but that's the idea. So the idea is that unless I'm literally in the eigenstate basis, the Hamiltonian will always look to me like a random matrix, even if I'm in a basis of states which is an epsilon away. That's kind of the idea of why random matrix theory enters in thinking chaos. And so if you put random matrix theory to work, you have a prediction for the probability of energy difference. And that probability distribution is very famous. It's called the Wigner-Dyson distribution. And we could just measure it, and we see that indeed our system obeys it. So there's level repulsion, just like I promised you. And it's also true that we sort of try to compare this, in what regime of couplings and truncations we have this Wigner-Dyson distribution versus an uncorrelated distribution, right, where energies are allowed to overlap. So we kind of took a measure of that. And what this is basically showing you is that at any coupling, doesn't matter how small it is, once you have your truncation becomes large enough, once you have enough particles, you wind up with a chaotic distribution. So it's basically the idea is that yes, maybe low particle number states are special, but once you have enough particles, you're chaotic. And so then we're in good shape. I mean, we know we have level repulsion, and so we might suspect that there should be a universality. That is to say, if we measure a local operator in some energy eigenstate, then we have a prediction for what it should behave like. It should behave like some coefficient times temperature to the appropriate power. And this is true when the temperature is much bigger than all the mass scales in the problem, right? And the nice thing about it is that first, we know what the power is. And two, because the CFT and the UV is just a free scalar, we can compute these numbers. So now we can compare this to our data. And what do we see? So here's, for example, a particular operator. I divided it by energy density squared because its dimension is 4. So this cancels the majority of the energy dependence. And we see that from here to here, it's roughly flat. It's roughly flat here as well. So this is a weak coupling. This is a strong coupling. But again, temperature is emergent in both cases. And also the value of this operator is very similar. It doesn't matter what the coupling is. The value should only be given for these high energy density states by this coefficient here, which doesn't care what the value of the coupling is. So you have a universality of expectation values, right? And now you can check something more detailed. So of course, there's deviations in the IR and deviations in the UV, and deviations in the IR and deviations in the UV, but there's a regime over which we kind of trust our data, over which there's a nice plateau. So we see, it seems like the temperature dependence for a huge number of states is correct. And now we can check something even more in detail, which is that we can check the coefficients, right? So it turns out that this combination of operators is in fact a primary operator. And a primary operator in the CFT cannot have an expectation value in 2D. And so we know that the expectation value of this operator has to be the same as the expectation value of this operator as we crank up the temperature. And so this is another numerical test that we can run. And again, we see that here are these two operators, a weak coupling, and so they kind of begin to approach each other as we go to larger and larger energy density or larger and larger temperature, just as we would have expected here. And even more detailed, we can look at the difference between them at weak coupling. And at weak coupling, you might guess that the dominant thing that violates the CFT answer comes from the mass and not from the coupling, just because the coupling is numerically small. And here I'm showing you our data, and the dashed line is the violation due to the mass, because if the violation is just from the mass, of course we could compute it, right? And so we see that the numerical data, as we increase the truncation, is agreeing better and better with this line.
Sorry, just to make sure I'm following. Temperature is hidden in epsilon here.
Right. It's basically temperature squared. So we have evidence that, you know, not only is there that there's a temperature that's emergent, but first of all, there's evidence that there's universality, but also that in fact there's an emergent. Okay, so I think that there are no questions about this. Nothing else to say. Okay, so maybe I'll say one more thing. Allow me like one more. Which is, we also found a set of states that that we don't completely understand, but seem to not be thermal state. So one thing you could, you know, if you could look at this expansion of our state, of an eigenstate in terms of our basis, and compare that to the prediction, and look at the statistics of these coefficients and compare that for each state, compare the statistics of its coefficients to the predictions of random matrix theory. So if they agree with random matrix theory, that means that the state is sort of thermal. If they don't agree with random matrix theory, maybe you think that there's some structure there. And so again, this is what we find numerically. So at weak couple or zero coupling, they do not agree. So this is the difference between this, what we compute numerically, and the expectation from random matrix theory. So here you see all kinds of structure, and indeed that's because it's a free theory and it has all kinds of sectors in it. At very strong coupling, there's very good agreement and essentially no exceptions. And at weak coupling, most of the data agrees, right? That's not surprising because we found that the statistics of energy levels obeys the level repulsion, but there's a whole bunch of states here that seem to not agree. And we're currently trying to understand what those states are. And I can tell you a little bit about them. So we tried to focus on these states and there are red ones and blue ones. And we computed various, so if they don't agree, that means that local operators should be able to distinguish them. And here the blue states do seem to be kind of outliers. The red ones are not for this operator. But for this operator, the red states really do seem to be different than the bulk of the distribution. And how would you explain that this particular operator has a different expectation for these states? Well, this operator is essentially measuring their energy. And it's basically telling you that the energy per particle of these states is low compared to what you'd expect in a typical thermal distribution. And so our conjecture was that these are states which are kind of non-relativistic. So we checked their approximate particle number, and we did see that they have approximate well-defined particle number. And so we're not exactly sure what they are, but it is known that non-relativistic bosons with a repulsive interaction, which is what you would get in the non-relativistic limit, are an integrable. That's an integrable system. And so to the extent that our truncation is not resolving their widths, right, or not resolving other irrelevant interactions that they are experiencing, we think that maybe that's the reason that we're seeing states. This is something we're trying to explore. And these states, which have very few particles but are very high energy, maybe they're scattering states. We're not sure exactly. But it's interesting, I guess, that the coefficient statistics are helping us understand well, at least focusing our attention on various observables and helping us navigate which states are thermal baths and which states possibly live longer. So that's all I have to say. So I hope I convinced you that Hamiltonian truncation is essentially helping you access regimes in quantum field theory that are difficult to get using other tools. This combination of CFT structure and the light cone we found to be empirically to be efficient. For example, in any apples to apples comparison, they're faster, better than box space methods. You could use the framework allows for non-Lagrangians, right? So you can deform, you just need the CFT data and you can deform with some operator. It doesn't necessarily have to be a Lagrangian theory. And in particular, for those of you who know what the fuzzy sphere are, there's a lot of data, CFT data coming from the fuzzy sphere for the 3D easing CFT. And so the same kind of theory that I showed you, which had those narrow resonances, its 3D cousin can now be explored and maybe something that we're thinking of doing next year. We took a first pass at high energy states. Eventually, we would like to see hydrodynamics emerge, but at least we saw that there does seem to be an emergent temperature in those states, and that eigenstate thermalization seems to be happening. And again, this is something that we can, with the fuzzy sphere, now check for in the 3D case. And other things we can do, which we have not done, is we can think about other quantum numbers, not just large energies, but there can also be large charges. So we can model chemical potentials. We can, in principle, try to understand superfluids, Fermi surfaces, and all this kind of thing. But it just requires working in a sector of a particular large fixed charge.
Maybe I missed it. So in ETH, the right-hand side was basically thermal expectation value where the thermal state is defined in your deformed theory, not the CFT, right?
Right.
But then in one of your expressions, that was actually replaced by CFT expectation.
Right, because at high temperature.
So that was for high temperature.
Yes.
Okay.
Exactly. It's only in the high temperature limit. Right.
And the place where you showed the rough agreement with the expected behavior was this high temperature region,
Yes.
large epsilon in your
Yeah,
location.
that's right. That's right.
Just coming back to the beginning, Sarah, we're just putting a large amount of momentum. Is there a difference between this approach and DLCQ?
So I mean, the large momentum limit is similar to DLCQ, but I guess the only thing I would say is that so for instance, in this kind of situation where I have a deformation by sigma, I don't know how to make sense of what we found in the DLCQ basis.
So if you directly try to,
Yes, if you try to do this, you would kind of see the DLCQ states decoupling. So that's basically because they are, they're almost like delta function support, right? But it's not that our particular basis states. You could use any smooth function, but literally DLCQ, which is kind of discontinuous, is not a good idea.
I see.
So it's some cases like 5 to the 4th, of course you can do DLCQ, people have, but this kind of sigma deformation, I don't know how to. What is the deal? I don't think that DLCQ is the right approach. Yeah.
I mean, connected to this, dimensionality, most of the examples were two-dimensional, but
Yeah.
you could in principle do this.
Yeah. Let me just give you, it's just, here's a 3D example. We did 3D 5 to the 4th. It's more expensive, it takes longer. But for instance, 3D 5 to the 4th, we tuned to criticality, we checked that operators that have the same quantum numbers all produce the same behavior in the IR, so there's universality. We don't have very good resolution because this has only 500 multiplets, basically conformal multiplets. So if you try to extract some kind of power law here, you get, I don't know, you get 2.4 instead of, the dimension of epsilon comes out to be 1.2 instead of 1.4. We don't have the resolution, but we definitely check that there's a universality. We check that the trace of the stress tensor vanishes at the easy CFT fixed point. We believe that it's sensible, but it's more expensive. So we always test our ideas first in lower dimensions, but yeah, we're working on higher dimensions.
You also had this plot for the, say, resonances for the non-interval Eisenfield theory.
Yeah,
If I remember correctly, there was some bootstrap result on these resonances by Gabayan in. Have you tried comparing?
on the resonances.
Yeah.
Right. I'm not sure if their method allowed them to measure the width of the resonance.
Really, I thought that this.
Did
would be
they?
bootstrap. Oh, maybe I misremember, but I thought that.
Oh, no, maybe you're right, because they were trying to compute it, it's a zero.
Right.
Yeah, it's a zero on the plane.
Right.
Yeah. So maybe there's some results for some of them. I have to remember what regime that was in. But, yeah, but to me, I think they were looking at, to me, what was surprising, I guess, is that, you see this narrow width in so many of them.
Right.
I think they were looking at the leading one.
I see.
It's kind of surprising. Anyway, yeah.
Yeah. I
Whatever, I
understand.
can't
Yeah.
make it work with that. But yeah, it's surprising that these high energy states would be so stable. Yeah, because their phase space of decay is even larger.
Actually, a question about the slide. You said you only understand the symmetry broken phase.
Yes.
But why was that?
Yeah, this is something that maybe I could get some help from people who think about fancy symmetries, but on the symmetry unbroken side, the fermions are not confined, right? And now I have to figure out, so now I have my chiral states should somehow include an odd number of fermions as well. And in fact, in the boosted data, when we literally took a theory on the circle and we began to boost it, we saw that, we needed that basically, well, there's the states built on the NS vacuum, and then there's the states built on the Ramon vacuum, and they're very close to each other in that regime, and you need to include them to get good results. But I'm not quite sure.
But they don't mix, right?
Yeah, so they do mix with each other in the sense that, so if I had to venture a guess, if I had to venture a guess, I think that what's missing is some kind of term where the sigma operator is replaced by the disorder. It seems to be like what would be the natural guess, but I don't know how to write down something which is gauge invariant. So this is something that would be useful in some sense, because a fermion by itself is a weird object. So no, yeah, so it's basically because I don't know how to include even number of fermion states, but in this phase I don't have to because they're confined. But I believe it's possible. Numerics suggest that there is a light cone effective Hamiltonian. We numerically, by taking, by doing something stupid, that is to say, taking states in a circle and looking at those states at higher and higher momentum, we have numerical evidence that this kind of object exists, but I don't know how to write some nice compact form. And if we could, then we could, of course, compute the other side of the phase transition. So even surprising, because I always thought that this is going to be the difficult side. Apparently it was the easiest.
If there are no more questions, let's thank Ami again.
On top second, by the way.
Yeah, I remember, yeah,